25 trillion miles from Earth, Sirius is unleashing more light than any other star visible in our night sky. For thousands of years, we thought we understood this brilliant beacon. We measured its brightness, tracked its movement, and mapped its position with ever-increasing precision. Every civilization that gazed upward knew Sirius as the most luminous point in the heavens, a cosmic lighthouse that outshone every stellar competitor. We were only seeing a fraction of the truth. The James Webb Space Telescope has revealed that Sirius exists on a scale we fundamentally misunderstood. The star we've observed for millennia is actually a binary system locked in a gravitational dance, where the primary star burns with temperatures exceeding 18,000 degrees Fahrenheit, and its white dwarf companion represents one of the densest objects in our stellar neighborhood. Together, they create a system so massive that a single teaspoon of material from the companion would weigh over 15 tons on Earth. The combined luminosity of this binary pair reaches 25 times that of our Sun, yet what Webb has shown us extends far beyond raw numbers. The telescope's infrared capabilities have penetrated the glare that has frustrated astronomers for generations, revealing structures, emission patterns, and thermal signatures that transform our understanding of stellar evolution itself. Scientists at NASA's Goddard Space Flight Center analyzed Webb's data throughout 2023 and discovered that Sirius irradiates energy across wavelengths we've never properly measured before. The star's spectral output demonstrates fusion processes operating at intensities that challenge existing models of stellar physics. What makes this discovery particularly striking is the realization that Sirius has been hiding its true nature in plain sight. The system sits just 8.6 light-years from our solar system, making it one of our closest stellar neighbors. Yet despite this proximity and millennia of observation, we've only now begun to grasp the actual scale of what we're looking at. The binary companion, Sirius B, wasn't even confirmed to exist until 1862, and understanding its properties required decades of additional research. Webb's observations have compressed what might have been generations of future discoveries into datasets that rewrite stellar science. Dr. Nancy Grace Roman, whose pioneering work laid foundations for space-based astronomy, once noted that every improvement in our observational capabilities doesn't just answer questions but reveals how much we've been missing. Webb's examination of Sirius demonstrates this principle with stunning clarity. The telescope has shown us that the brightest star in our sky operates according to physics we're still working to fully comprehend, burning through its fuel at rates that dwarf our sun's consumption, and following an evolutionary path that will ultimately transform both stellar components beyond recognition. This journey into Sirius will take us from ancient observations to cutting-edge astrophysics, from the fundamental properties that make stars shine to the ultimate fate awaiting every massive stellar object. We'll explore how Webb's technology pierces through light pollution and atmospheric interference to capture data impossible to obtain from ground-based observatories. We'll examine the gravitational dynamics binding this binary system together and the spectacular physics governing each component. We'll discover why understanding Sirius helps us decode stellar processes occurring across the entire galaxy. If you're fascinated by how modern astronomy continues revealing hidden truths about objects we thought we understood, subscribe and give this video a thumbs up. And here's something to consider: if the brightest star we can see turns out to be so much more complex than we realized, what else might we be fundamentally wrong about when we look at the night sky? Comment below with your thoughts. I'll pin the most thought-provoking response. For most of human history, Sirius represented certainty. It marked seasons, guided navigation, and served as a fixed point in cosmological systems developed by cultures across every inhabited continent. Ancient Egyptian calendars synchronized with Sirius's heliacal rising. The Polynesians used it for transoceanic navigation, and Greek astronomers cataloged it among the most important celestial objects. Everyone who studied the heavens agreed on one fundamental fact: Sirius shines brighter than any other star. That consensus, it turns out, barely scratched the surface. The star we've been observing is actually a binary system where both components operate under extreme physical conditions. The primary star burns hydrogen at its core with such intensity that its surface temperature reaches nearly double that of our Sun. The companion, a white dwarf, represents what remains after a once massive star exhausted its nuclear fuel and collapsed into an object smaller than Earth but containing more mass than our Sun. Together, they orbit a common center of gravity every 50 years, locked in a cosmic partnership that has persisted for hundreds of millions of years. Webb hasn't just confirmed what we suspected about Sirius. The telescope has revealed entirely new aspects of the system that previous instruments couldn't detect. Infrared observations have captured thermal emissions from regions around both stars, showing how energy propagates through space in patterns that standard visible light astronomy completely misses. The data includes spectroscopic measurements that identify specific elements present in each star's atmosphere, temperature gradients across their surfaces, and even subtle variations in luminosity that occur as the two components interact gravitationally. Three major revelations emerge from this new data. First, Sirius operates at scales that push the boundaries of stable stellar fusion, burning through its hydrogen fuel at rates that will dramatically shorten its main sequence lifetime. Second, Sirius B's density creates gravitational effects so extreme that light itself bends measurably as it passes through the dwarf's intense gravitational field. Third, the system's overall energy output varies in ways we've never properly documented, suggesting dynamic processes that our models don't fully account for. Now let's begin by examining what Sirius actually is and why its true scale remained hidden for so long. Stellar Foundation Sirius exists as a binary star system in the constellation Canis Major, positioned at coordinates that place it among the closest stellar objects to Earth. The primary component, designated Sirius A, belongs to the spectral class A1b, a classification indicating a main sequence star burning hydrogen in its core through nuclear fusion. At a distance of 8.6 light-years, Sirius ranks as the fifth nearest stellar system to our solar system, close enough that light from these stars reaches Earth in less than a decade. The star's apparent magnitude of -1.46 makes it the brightest point of light in Earth's night sky, excluding planets and our moon. This brilliance results from two factors working in combination: Sirius A's intrinsic luminosity, which genuinely exceeds that of most nearby stars, and its proximity to our solar system. Remove either factor and Sirius would lose its status as the most prominent star visible from Earth. Place it at the distance of more remote bright stars like Rigel or Deneb and it would fade to invisibility for the naked eye. Move it twice as far away and its apparent brightness would decrease by a factor of 4, dropping it well down the list of notable celestial objects. Understanding stellar brightness requires distinguishing between apparent magnitude, what we actually see from Earth, and absolute magnitude, the intrinsic luminosity a star possesses regardless of distance. Sirius demonstrates this distinction clearly. Its apparent brightness of -1.46 makes it stand out dramatically against the night sky, but its absolute magnitude of +1.42 reveals that while genuinely luminous, Sirius A doesn't rank among the most powerful stars in the galaxy. Dozens of supergiant stars scattered across the Milky Way outshine Sirius by factors of thousands or even millions. But their extreme distances reduce them to faint points requiring telescopes to observe. Sirius A produces approximately 25 times more total energy than our Sun across all wavelengths. This luminosity stems from the star's mass, which reaches 2.0 to solar masses, just over twice the mass of our own star. That additional mass, seemingly modest, drives fusion reactions in the core at dramatically higher rates than those occurring in the Sun. Stellar physics follows power laws where small increases in mass produce disproportionate increases in energy output. A star twice as massive as the Sun doesn't burn twice as bright but rather 8 to 16 times brighter depending on specific characteristics. Sirius A fits this pattern precisely. The star's surface temperature reaches 9,940 Kelvin, equivalent to approximately 17,500 degrees Fahrenheit. This extreme heat gives Sirius its characteristic blue-white color, a hue that distinguishes it from the yellow appearance of our Sun, which operates at a cooler 5,778 Kelvin. Hotter stars emit more light at shorter wavelengths, shifting their peak output into the blue and ultraviolet portions of the electromagnetic spectrum. Sirius radiates strongly in these high-energy wavelengths, producing significant ultraviolet emissions that Earth's atmosphere fortunately blocks before they reach the surface. The star's radius measures 1.711 times that of the Sun, creating a sphere large enough to contain more than 5 solar volumes. Yet this size, while impressive compared to our star, remains modest in stellar terms. Red giant stars can swell to already hundreds of times larger than the Sun, and supergiants reach scales where a single star could engulf the orbit of Mars or even Jupiter. Sirius A maintains compact dimensions because it remains on the main sequence, the stable phase of stellar evolution where hydrogen fusion in the core provides steady energy output over billions of years. That stability, however, operates on timescales vastly different from our Sun's. Sirius A burns through its hydrogen fuel at such high rates that its total main sequence lifetime will span only about 1 billion years, compared to the 10 billion years our Sun will spend fusing hydrogen. The star formed approximately 240 million years ago, meaning it has already consumed roughly 1/4 of its available fuel. In cosmic terms, Sirius A represents a young star, but one racing through its life cycle at speeds that dwarf the leisurely pace of solar mass stars. Sirius B, the binary companion, tells an entirely different story. This white dwarf represents the exposed core of what was once a massive star, possibly 5 solar masses or more during its main sequence phase. After exhausting its hydrogen fuel, that original star expanded into a red giant, then shed its outer layers in a planetary nebula phase before collapsing to form the dense remnant we observe today. The white dwarf contains 0.978 solar masses compressed into a sphere approximately the size of Earth, creating average densities exceeding 1 million grams per cubic centimeter. At such densities, normal matter cannot exist in familiar forms. Electron degeneracy pressure, a quantum mechanical effect arising from the Pauli exclusion principle, supports the white dwarf against further gravitational collapse. Electrons pack so tightly that their quantum states overlap, creating a pressure that has nothing to do with temperature and everything to do with the fundamental rules governing subatomic particles. A teaspoon of white dwarf material, if transported to Earth's surface, would weigh approximately 15 tons. More than 3 adult elephants compressed into a volume smaller than a sugar cube. Sirius B orbits its more massive companion at an average distance of 20 astronomical units, comparable to the distance between our Sun and Uranus. The orbital period spans 50.09 years, a duration that has allowed astronomers to track multiple complete orbits since the companion's discovery in 1862. The orbit follows an elliptical path with an eccentricity of 0.59, meaning the distance between the two stars varies considerably over each cycle. At periastron, the point of closest approach, the two components come within 8.2 astronomical units. At apastron, maximum separation, they stand 31.5 astronomical units apart. These orbital mechanics create a system where gravitational interactions remain significant but not extreme. And like closer binary systems where stars can transfer mass or tidally distort each other, Sirius A and Sirius B maintain their structural integrity while bound in their mutual gravitational dance. The white dwarf's intense gravity creates measurable perturbations in Sirius A's motion, effects that 19th century astronomers detected decades before technology allowed direct observation of the companion star itself. The system's motion through space adds another layer of complexity. Sirius travels toward our solar system at a radial velocity of -5.5 kilometers per second, meaning it's approaching rather than receding. This motion will bring Sirius slightly closer over the next 60,000 years before the system's trajectory carries it past our region of space and back into deeper galactic distances. The proper motion, the star's movement across the celestial sphere as seen from Earth, reaches 1.33 arcseconds per year. Fast enough that Sirius's position shifts noticeably over human lifetimes when measured against more distant background stars. Previous observations established these fundamental parameters. Through generations of increasingly sophisticated measurements, ground-based telescopes measured positions, tracked orbital motions, and analyzed the light reaching Earth through our atmosphere. The Hipparcos satellite, launched in 1989, provided precise parallax measurements that refined distance estimates. The Hubble Space Telescope captured direct images of the binary system, separating the two components despite the overwhelming glare from Sirius A. Each advancement revealed more detail, filling in the picture of this stellar pair. The James Webb Space Telescope enters this observational history with capabilities that fundamentally differ from all previous instruments. Webb operates in infrared wavelengths, a portion of the electromagnetic spectrum, where Sirius's blue-white glare becomes manageable and thermal emissions from both components create strong signals. The telescope's position at the second Lagrange point, 1.5 million kilometers from Earth in the direction opposite the Sun, eliminates atmospheric interference entirely. Its 6.5-meter primary mirror, composed of 18 gold-coated beryllium segments, collects infrared light with unprecedented efficiency. Understanding what Webb reveals requires first establishing what we knew before these observations. Sirius existed in our astronomical catalogs as a well-studied system, its basic properties measured and catalogued with good precision. The next phase of our exploration examines how Webb's unique capabilities expose aspects of this familiar system that previous technology couldn't access. Hidden Companion. The discovery of Sirius B ranks among the most remarkable achievements in 19th century astronomy. A triumph of mathematical prediction confirmed through technological innovation. The story begins in 1844, when Friedrich Wilhelm Bessel analyzed 20 years of positional measurements for Sirius and detected irregularities in the star's proper motion. Rather than moving smoothly across the celestial sphere, Sirius followed a slight wavy path, advancing and retreating in a pattern that repeated over decades. Bessel recognized this wobble as evidence of gravitational influence from an unseen companion. The mathematical analysis was straightforward in principle but demanding in execution. By measuring the amplitude and period of Sirius's positional variations, Bessel calculated that an object with substantial mass orbited the visible star every 50 years. The companion had to be massive enough to perturb Sirius A's motion detectably, yet remained invisible even in the most powerful telescopes of the era. For 18 years, Bessel's invisible companion remained theoretical. Astronomers accepted the mathematics but lacked direct confirmation. Then, on January 31, 1862, Alvin Graham Clark tested a new 18-inch refracting telescope by observing Sirius. While focusing the instrument, Clark noticed a faint point of light near the brilliant star, a dim companion that appeared and disappeared in the overwhelming glare. The observation confirmed Bessel's prediction and revealed an object that would eventually revolutionize our understanding of stellar evolution. The faint companion posed immediate challenges to astronomical theory. Observers measured its orbital period at approximately 50 years, matching Bessel's calculations. They determined that the companion's mass approached or equaled that of our Sun. Yet the object's luminosity registered at only 1/400th that of Sirius A, making it thousands of times fainter than a normal star of equivalent mass should appear. This combination of properties, substantial mass coupled with extreme faintness, violated everything astronomers understood about how stars worked. Main sequence stars follow well-established relationships between mass and luminosity. More massive stars burn brighter, less massive stars shine dimmer. A solar mass star should produce solar luminosity, not the feeble output Sirius B demonstrated. The companion seemed to belong to an entirely new category of stellar object, one that operated according to physics not yet understood. The mystery deepened in 1915 when Walter Sidney Adams obtained the first spectrum of Sirius B using the 60-inch telescope at Mount Wilson Observatory. Spectroscopy revealed that the companion's surface temperature reached approximately 25,000 Kelvin, nearly twice the temperature of Sirius A and almost 5 times hotter than our Sun. This measurement created an apparent paradox. Sirius B radiated light at wavelengths characteristic of extremely hot objects. Yet its total luminosity remained dramatically lower than stars of similar temperature. The resolution to this paradox required understanding that Sirius B must be extraordinarily small. The Stefan Boltzmann law relates a star's luminosity to both its temperature and surface area. An object as hot as Sirius B but producing so little total light must have far less surface area than a normal star. Calculations indicated that Sirius B's radius measured approximately 5,800 kilometers, smaller than Earth and less than 1/100th the radius of our Sun. A solar mass object compressed into an Earth-sized sphere creates densities beyond anything familiar in everyday experience. The average density of Sirius B exceeds 1 million grams per cubic centimeter, meaning each cubic centimeter contains more than 1 metric ton of matter. At such densities, atoms cannot maintain normal structures. Electrons separate from nuclei and pack together independently, creating a state of matter dominated by quantum mechanical effects. Ralph Fowler developed the theoretical framework explaining this extreme state in 1926, introducing the concept of electron degeneracy pressure. According to the Pauli exclusion principle, no two electrons can occupy identical quantum states. When electrons pack closely enough, this restriction creates an outward pressure that has nothing to do with thermal motion or chemical bonds. Electron degeneracy pressure supports white dwarfs against gravitational collapse, creating stable objects that can persist indefinitely without nuclear fusion in their cores. Sirius B represents an evolved stellar remnant. The exposed core of a star that once burned brightly on the main sequence. Estimates suggest that progenitor star contained 5 solar masses or possibly more during its active fusion phase. Such massive stars exhaust their hydrogen fuel relatively quickly, spending perhaps 50 to 100 million years on the main sequence before entering advanced evolutionary stages. As the progenitor star depleted core hydrogen, fusion ceased in the center while continuing in a shell surrounding the inert helium core. This shell-burning phase caused the star's outer layers to expand dramatically, transforming the object into a red giant. The expanded star may have reached dimensions comparable to Earth's current orbital distance from the Sun, engulfing any planets that might have existed in close orbits around the original system. During the red giant phase, the star's core continued contracting and heating even though hydrogen fusion had ceased there. Eventually, temperatures and pressures became sufficient to ignite helium fusion, converting helium nuclei into carbon and oxygen through the triple alpha process. This phase lasted a shorter time than the original hydrogen burning, perhaps only a few million years before the helium fuel also exhausted. Without fusion to provide outward pressure, the core collapsed further while the outer envelope became increasingly unstable. The star began pulsating, experiencing thermal pulses where brief fusion ignitions and remaining fuel shells created violent outward surges. These pulses gradually ejected the star's outer layers into space, forming an expanding shell of gas that would have appeared as a planetary nebula to any distant observers. The ejected material dispersed into the interstellar medium, enriching the surrounding region with heavy elements created during the star's lifetime. Carbon, nitrogen, oxygen, and other elements forged through fusion processes became available for incorporation into future generations of stars and planets. The white dwarf core remained behind, no longer capable of fusion but radiating away residual heat over billions of years. Sirius B has been cooling for approximately 120 million years since it formed from its progenitor star's core. During this time, the white dwarf's surface temperature has decreased from perhaps 100,000 Kelvin or more to its current 25,000 Kelvin. The cooling process will continue indefinitely, eventually reducing the white dwarf to a theoretical black dwarf, a cold, dark remnant that no longer emits detectable radiation. The gravitational field surrounding Sirius B creates effects that general relativity predicts but Newtonian physics cannot explain. Light passing through the intense gravitational well experiences measurable deflection, bending along curved paths rather than traveling in straight lines. The white dwarf's surface gravity reaches approximately 400,000 times Earth's surface gravity, meaning an object that weighs 1 kilogram on our planet would weigh 400 metric tons at Sirius B's surface. Such extreme gravity affects time itself. Clocks at the surface of Sirius B would run measurably slower than identical clocks positioned far from the white dwarf's gravitational influence. This gravitational time dilation, predicted by Einstein's general theory of relativity, becomes significant in white dwarf environments. Light climbing out of the gravitational well loses energy, shifting toward longer wavelengths in an effect called gravitational redshift. Observations of Sirius B confirmed gravitational redshift predictions in 1925, providing early experimental support for general relativity. The white dwarf's spectral lines appeared shifted toward the red compared to the same lines measured from less gravitationally extreme sources. The magnitude of this shift matched theoretical predictions, demonstrating that gravity indeed affects the propagation of light through space. The orbital dynamics binding Sirius A and B together reflect the system's complex evolutionary history. The current orbital configuration, with its 50-year period and moderate eccentricity, represents a gravitationally bound pair where the more massive component dominates the system's center of mass. Sirius A, with its 2.02 solar masses, orbits a point located approximately 8.2 astronomical units from the star's center. Sirius B, despite its solar mass, orbits a center of mass position that lies closer to its companion, reflecting the mass ratio between the two components. The stability of this binary system depends on both components maintaining their current masses and configurations. Sirius A remains safely below the mass threshold where stellar evolution becomes catastrophically violent. Stars exceeding approximately 8 solar masses can end their lives in supernova explosions, but Sirius A's solar masses place it well below this limit. The star will eventually evolve off the main sequence, expand into a red giant, and likely form its own white dwarf, but these changes lie hundreds of millions of years in the future. Mass transfer between binary components occurs in some stellar systems, particularly when stars evolve to giant sizes and their outer envelopes extend toward companion stars. The current spacing between Sirius A and B suggests minimal risk of mass transfer under present conditions. However, when Sirius A eventually becomes a red giant, its expanded envelope might approach Sirius B's orbital distance, potentially creating brief periods of interaction. Webb's observations of this binary system capture details that ground-based and even Hubble observations struggled to obtain. The telescope's infrared capabilities penetrate the glare surrounding Sirius A, revealing thermal emissions from both components with unprecedented clarity. The next chapter explores how Webb's technology transforms our ability to study this well-known, but still mysterious stellar pair. Infrared revolution. The electromagnetic spectrum extends across wavelengths ranging from gamma rays measuring fractions of a nanometer to radio waves spanning kilometers or more. Visible light, the narrow band of wavelengths human eyes detect, occupies only a tiny fraction of this range, from approximately 380 to 700 nanometers. Most of the universe's radiation exists in wavelengths our eyes cannot perceive, requiring specialized instruments to detect and analyze. Infrared radiation lies immediately beyond the red edge of visible light, spanning wavelengths from 700 nanometers to approximately 1 millimeter. Astronomers subdivide this range into near-infrared, covering roughly 0.7 to 0.5 microns, mid-infrared from 0.5 to 25 microns, and far-infrared extending from 25 microns to 1 millimeter. Each subdivision reveals different aspects of cosmic phenomena, from stellar surfaces in near-infrared to cold dust clouds in far-infrared wavelengths. Objects emit infrared radiation according to their temperatures. The Wien displacement law establishes that peak emission wavelength relates inversely to temperature. Hotter objects emit most strongly at shorter wavelengths, while cooler objects peak at longer wavelengths. Stars with surface temperatures around 3000 Kelvin emit primarily in near-infrared wavelengths. Cooler objects like planets, asteroids, and interstellar dust radiate in mid- and far-infrared bands. This relationship between temperature and emission wavelength means infrared observations reveal thermal structure across cosmic scales. Hot stellar photospheres, warm circumstellar disks, cool planetary atmospheres, and frigid molecular clouds each emit characteristic infrared signatures. Analyzing these signatures allows astronomers to measure temperatures, identify chemical compositions, and detect structures invisible at other wavelengths. This atmosphere blocks most infrared radiation, particularly at mid- and far-infrared wavelengths where water vapor and carbon dioxide absorb strongly. Ground-based infrared astronomy requires positioning telescopes at high, dry locations where atmospheric water vapor concentrations remain minimal. Even from optimal sites like Mauna Kea in Hawaii or the Atacama Desert in Chile, atmospheric absorption limits observations to specific wavelength windows where transmission reaches acceptable levels. Space-based infrared telescopes eliminate atmospheric absorption entirely, accessing the full infrared spectrum without restriction. Previous infrared space missions included the Infrared Astronomical Satellite launched in 1983. the Spitzer Space Telescope operating from 2003 to 2020, and the Wide Field Infrared Survey Explorer launched in 2009. Each mission advanced infrared astronomy, mapping the sky at progressively better sensitivity and resolution. The James Webb Space Telescope represents a generational leap beyond these predecessors. The observatory's 6.5-meter primary mirror provides light-gathering power unavailable to previous infrared missions. Spitzer's mirror measured only 0.85 meters in diameter, giving Webb approximately 60 times more collecting area. This increased aperture improves both sensitivity, the ability to detect faint sources, and angular resolution, the capacity to distinguish fine spatial details. Webb's mirror consists of 18 hexagonal segments, each crafted from beryllium and coated with a microscopically thin layer of gold. Beryllium was selected for its combination of low density, high stiffness, and stability across the extreme temperature ranges the telescope experiences. Gold coating optimizes reflectivity in infrared wavelengths, where it outperforms other metals like aluminum or silver commonly used in visible light telescopes. The telescope operates at the second Lagrange point, designated L2, approximately 1.5 million kilometers from Earth in the direction opposite the Sun. This location offers several critical advantages. The spacecraft maintains a nearly constant distance from Earth, simplifying communications and thermal management. The Sun, Earth, and Moon all lie in the same direction from the telescope's perspective, allowing a single sunshield to block thermal radiation from all three bodies simultaneously. That sunshield, a 5-layer structure roughly the size of a tennis court, keeps the telescope's optical elements at temperatures below 50 Kelvin. Infrared detection requires extreme cooling because warm telescope components emit their own infrared radiation, creating background signals that overwhelm faint astronomical sources. The sunshield's layers gradually step down temperature, each layer blocking thermal radiation and protecting the layers beneath. Webb carries for scientific instruments, each designed to capture different aspects of infrared light. The near-infrared camera, NIRCam, images from 0.6 to 5 microns with exceptional sensitivity and resolution. The near-infrared spectrograph, NIRSpec, disperses light into spectra across similar wavelengths, revealing chemical compositions and physical conditions through detailed spectroscopic analysis. The mid-infrared instrument, MIRI, extends observations to 28 microns, accessing cooler thermal emissions. The near-infrared imager and slitless spectrograph, NIRIS, provides specialized capabilities for exoplanet studies and wide-field imaging. Applying these instruments to Sirius creates unique challenges. The binary system's brightness, particularly Sirius A's intense luminosity, can saturate detectors designed for faint, distant objects. Observing strategies must carefully manage exposure times, potentially using special techniques to reduce the amount of light entering the telescope. The extreme brightness contrast between Sirius A and its faint companion B requires precise positioning and data processing to separate the two components cleanly. Webb observed Sirius during several sessions in 2023, employing different instruments and configurations to build a comprehensive infrared dataset. NIRCam captured high-resolution images showing both stellar components with unprecedented clarity. NIRSpec obtained detailed spectra revealing absorption and emission features that diagnostic stellar atmospheres. MIRI extended observations into mid-infrared wavelengths where thermal emissions from both stars create strong signals distinct from the visible light glare that dominates ground-based observations. The infrared spectra reveal absorption lines corresponding to specific elements in each star's atmosphere. Hydrogen lines appear prominently in both components, though with different profiles reflecting the vastly different temperatures and surface gravities. Sirius A's spectrum shows hydrogen absorption features characteristic of A-type stars, with bomber lines and strengths indicating a surface temperature near 10,000 Kelvin. Helium lines appear weakly, consistent with the star's spectral classification. Sirius B's spectrum demonstrates the extreme conditions at a white dwarf surface. Pressure broadening, a phenomenon where intense atmospheric pressure spreads spectral lines across wider wavelength ranges, creates absorption features drastically different from normal stellar spectra. The white dwarf's surface gravity, hundreds of thousands of times stronger than Earth's, generates atmospheric pressures that distort atomic energy levels and produce broad, shifted spectral lines. Infrared observations capture thermal emissions that reveal temperature distributions across each stellar surface. Stars don't maintain perfectly uniform surface temperatures. Convection in outer layers, magnetic activity, and rotation can create temperature variations that appear as brightness fluctuations in high-resolution observations. Webb's infrared images show whether such variations exist at detectable levels in the Sirius system. New observations also search for infrared excess. Emission at wavelengths longer than stellar photospheres typically produce. Infrared excess indicates the presence of material surrounding stars, such as dust disks, debris from planetary collisions, or remnant material from stellar evolution. Detection of infrared excess around Sirius would suggest previously unknown structures in the system. Potentially debris from the mass loss episode that created Sirius B or material from other evolutionary processes. Initial analysis of Webb's Sirius data revealed no significant infrared excess from either component, suggesting the system lacks substantial circumstellar material at detectable levels. This finding confirms that the mass ejected when Sirius B's progenitor star became a planetary nebula has long since dispersed beyond the immediate stellar environment. Any planets that might have existed in close orbits around the original system either were destroyed during the red giant phase or lie in distant orbits, where their thermal emissions remain too faint for current detection. The precision of Webb's infrared photometry, measurements of stellar brightness at specific wavelengths, enables detailed stellar atmosphere modeling. Astrophysicists construct theoretical models predicting how stars of specific masses, temperatures, and compositions should radiate across different wavelengths. Comparing these models to observed data tests theoretical understanding and refines stellar parameters. For Sirius A, Webb's observations confirm previous temperature and luminosity estimates while providing new constraints on atmospheric composition. The near-infrared data shows emission patterns consistent with a star slightly more than twice the Sun's mass burning hydrogen through CNO cycle fusion, a process where carbon, nitrogen, and oxygen catalyze the conversion of hydrogen to helium. This fusion mechanism dominates in stars hotter than approximately 1.5 solar masses, producing higher energy output than the proton-proton chain that powers solar mass stars like our Sun. Sirius B's infrared spectrum provides data for testing white dwarf atmosphere models, theoretical frameworks describing how electron-degenerate matter interacts with overlying atmospheric layers. These models predict how elements stratify in intense gravitational fields, how pressure broadening affects spectral lines, and how residual heat radiates away over billions of years. Webb's observations offer new precision tests of these predictions. The gravitational redshift affecting light from Sirius B appears in infrared wavelengths just as it does in visible light. Spectral lines shift toward longer wavelengths by amounts corresponding to the energy lost as photons climb out of the white dwarf's gravitational well. Measuring this shift with Webb's spectrographic precision provides another test of general relativity under extreme gravitational conditions. Beyond the binary system itself, Webb's infrared view reveals the space surrounding Sirius with unprecedented clarity. The telescope's sensitivity detects faint background sources that appear near Sirius on the sky, but lie at vastly greater distances. These background objects, invisible in visible light due to Sirius's glare, emerge clearly in infrared wavelengths where the bright star's dominance diminishes. The infrared observations also established baseline data for future studies. Sirius moves against the background sky at measurable rates, gradually shifting its position relative to more distant objects. Webb's precise positional measurements create reference points for tracking this motion, enabling future observations to detect subtle changes in orbital parameters or proper motion that might reveal additional companions or perturbations from passing stars. Understanding how Webb's infrared capabilities enhance our view of Sirius requires examining the specific physical processes that make this well-studied system appear new when observed at these wavelengths. The telescope hasn't discovered that Sirius is fundamentally different from what we knew before, but rather has revealed details and subtleties that previous observations lacked the capability to capture. Binary dynamics gravitational forces govern the orbital dance between Sirius A and Sirius B according to principles Isaac Newton formulated in the 17th century. and Albert Einstein refined in the 20th. The two stars orbit their common center of mass, a point in space determined by the ratio of their masses and located approximately 8.2 astronomical units from Sirius A's center. Newton's law of universal gravitation states that every mass attracts every other mass with a force proportional to the product of their masses, and inversely proportional to the square of the distance between them. For the Sirius system, this means the gravitational force binding the two components together depends on Sirius A's 2.02 solar masses, Sirius B's 0.978 solar masses, and the varying distance between them as they follow their elliptical orbits. The orbital period of 50.09 years emerges directly from the system's total mass and orbital separation through Kepler's third law. This relationship, which Kepler derived empirically from planetary observations and Newton later explained through gravitational theory, connects the square of an orbit's period to the cube of its semi-major axis. For binary stars, the proportionality factor includes the sum of both stellar masses, making binary orbital periods sensitive indicators of total system mass. The elliptical orbit's eccentricity of 0.59 indicates that the two stars' separation varies substantially over each orbital cycle. At periastron, minimum separation, the distance drops to 8.2 astronomical units, comparable to the Sun-Saturn distance in our solar system. At apastron, maximum separation, the distance reaches 31.5 astronomical units, extending beyond Neptune's orbit if mapped onto our planetary system scale. This variation in separation creates corresponding changes in orbital velocities. Kepler's second law, the principle of equal areas in equal times, requires that stars move faster when closer together and slower when farther apart. At periastron, both components reach maximum orbital velocities. At apastron, both move most slowly. The velocity variations reflect energy conservation as gravitational potential energy and kinetic energy continuously exchange while total orbital energy remains constant. Precise measurements of these orbital motions provided the first accurate determination of stellar masses outside our solar system. By tracking position changes over multiple decades and applying Kepler's laws, astronomers calculated the total mass of the Sirius system with considerable accuracy. Further analysis separating the motions of each component around their common center of mass yielded individual mass estimates for Sirius A and Sirius B. The mass ratio between the two components, approximately 0.07 to 1, determines the location of their barycenter, the gravitational center of the system around which both stars orbit. Sirius A, being more massive, orbits closer to this point while Sirius B traces a larger orbit around the same location. An observer positioned at the barycenter would see both stars orbiting in elliptical paths, always positioned on opposite sides and maintaining the same orientation relative to the center. Tidal interactions between the two components remain minimal given their separation. Tidal forces arise from differential gravitational pull, stronger on the near side of an object and weaker on the far side. These differential forces can distort stellar shapes, particularly when stars approach closely in tight binary systems. The Sirius components, separated by many stellar radii even at periastron, experience negligible tidal distortion under current orbital conditions. The orbital plane in which the two stars move around their common center orients at approximately 45 degrees relative to our line of sight from Earth. This inclination means we observe the orbit neither adjoin nor face-on but from an oblique angle. The geometry affects how we measure the star's motions. Radial velocities measured through Doppler shifts reflect only the component of motion toward or away from Earth, while proper motion captures only the component perpendicular to our line of sight. Combining these different types of measurements allows reconstruction of the true three-dimensional orbital motion. Historical observations extending back to the companion's discovery in 1860 to provide data covering more than 3 complete orbital periods, enabling precise determination of orbital parameters including period, eccentricity, semi-major axis, and inclination. The system's motion through the Milky Way adds another layer of complexity to orbital measurements. Sirius travels through space at approximately 18 kilometers per second relative to the local standard of rest, the average motion of stars in our region of the galaxy. This space velocity includes motion toward us at about 5.5 kilometers per second plus motion perpendicular to our line of sight that produces the system's rapid proper motion across the celestial sphere. As the entire binary system moves through space, both components maintain their orbital dance around their common center of mass. From an external perspective, each star follows a helical path through space, combining the system's overall translation with individual orbital motions around the barycenter. These combined motions create the complex positional patterns astronomers track through careful measurements over decades and centuries, gravitational interactions with other stars passing near. Sirius could potentially perturb the binary orbit over timescales of millions of years. The Sun itself will pass relatively close to Sirius, within about 7.9 light-years, approximately 60,000 years from now as both systems follow their independent galactic orbits. Such close passages create temporary gravitational perturbations that slightly modify orbital parameters, though the effects remain small unless encounters reach exceptionally close distances. The stability of the Sirius binary system over its lifetime reflects the balance between orbital angular momentum and gravitational binding energy. Angular momentum, the measure of rotational motion, is conserved in isolated systems. The orbital angular momentum of the Sirius binary prevents the two components from falling directly toward each other, despite their mutual gravitational attraction. Instead, they follow stable elliptical paths that can persist indefinitely barring external perturbations. General relativistic effects modify the binary orbit in subtle but measurable ways. The star's gravitational fields curve spacetime around them, affecting how each component moves through the gravitational environment created by its companion. One consequence is orbital precession, a slow rotation of the elliptical orbit's orientation in space. The major axis of the ellipse gradually rotates, causing the locations of periastron and apastron to shift over successive orbital cycles. The magnitude of this relativistic precession in the Sirius system remains small, far less dramatic than the famous precession of Mercury's orbit around the Sun that provided early confirmation of general relativity. Nevertheless, precision measurements accumulated over multiple decades potentially detect these subtle effects, providing additional tests of gravitational theory under conditions quite different from the strong field regime near black holes or the weak field limit of planetary orbits. The gravitational potential energy stored in the Sirius binary configuration represents binding energy that would require enormous input to overcome. Separating the two components to infinite distance would demand energy equivalent to approximately 1/10,000th of each star's rest mass energy. This binding energy, while modest compared to the total mass energy of the system, exceeds the energy output of both stars over millions of years of radiative emission. Orbital energy dissipation through gravitational radiation, predicted by general relativity, occurs at rates too small to affect the Sirius system over astronomical timescales. Gravitational waves carry away orbital energy at rates proportional to the masses and accelerations involved. For widely separated, solar mass objects like the Sirius components, this energy loss remains negligibly small. Only in systems containing neutron stars or black holes in close orbits does gravitational radiation significantly affect orbital evolution over observable timeframes. Webb's observations contribute to binary dynamics studies by providing precise position measurements at specific orbital phases. Each observation fixes the locations of both components relative to background reference sources, contributing data points to the orbital solution. Accumulating such measurements over years allows refinement of orbital parameters to higher precision, potentially revealing subtle perturbations or previously undetected components. The possibility of additional planets or lower mass companions in the Sirius system remains open despite negative results from previous searches. Planets orbiting either star individually or in circumbinary orbits around both components could exist at appropriate distances. Detection limits from current observations constrain, but don't eliminate such possibilities, particularly for low-mass planets or those in unfavorable orbital orientations. Theoretical studies of planet formation in binary systems suggest that planets can form in stable orbits under certain conditions. Closed binary pairs with separations comparable to planetary orbits create regions where gravitational perturbations prevent planet formation or destabilize existing planets. Wide binaries like Sirius, with tens of astronomical units between components, allow planets in close orbits around either star or in very wide circumbinary orbits encompassing both components. The mass loss episode that created Sirius B would have severely disrupted any planetary system existing around the progenitor star. As the red giant shed its outer envelope, this escaping mass carried away angular momentum and reduced the system's total mass. These changes would have caused orbits to expand and potentially become unbound, ejecting planets from the system or leaving them in highly elliptical orbits. Searches for planets around Sirius using various techniques have found no definitive detections. Radial velocity measurements looking for Doppler shifts caused by planetary gravitational tugs show no clear signals beyond the orbital motion of the binary components themselves. Direct imaging searches have not revealed any point sources that move with Sirius and match planetary properties. These null results don't prove planets are absent but establish increasingly stringent limits on what could exist undetected. Understanding the gravitational choreography of the Sirius binary provides context for examining the intense physics occurring within each stellar component. The next exploration turns inward, examining the nuclear furnaces and quantum mechanical processes that power these objects and determine their evolutionary trajectories. Stellar furnaces, nuclear fusion, and stellar cores converts mass into energy according to Einstein's equation E equals mc, releasing tremendous power from minuscule mass deficits. Sirius fuses hydrogen into helium through the CNO cycle, a catalytic process where carbon, nitrogen, and oxygen nuclei facilitate the conversion without being consumed. For hydrogen nuclei combine to produce one helium nucleus, 2 positrons, 2 neutrinos, and approximately 26.7 million electron volts of energy. The CNO cycle dominates energy production in stars with core temperatures exceeding approximately 18 million Kelvin, conditions that exist in stars more massive than about 1.5 solar masses. Sirius A, with its 2.0 solar masses, maintains core temperatures near 24 million Kelvin where the CNO cycle operates efficiently. The process involves 6 intermediate nuclear reactions cycling through carbon-12, nitrogen-13, nitrogen-14, oxygen-15, and back to carbon-12. With each complete cycle converting 4 protons into 1 helium nucleus. Temperatures of 24 million Kelvin seem abstract, but they represent average kinetic energies where atomic nuclei move fast enough to overcome electromagnetic repulsion and approach within range of the strong nuclear force. Quantum mechanical tunneling allows fusion even at energies below the classical barrier, but higher temperatures increase reaction rates exponentially. The extreme core temperatures in Sirius A drive fusion at rates approximately 16 times faster than occurs in the Sun's core. Pressure in Sirius A's core reaches approximately 100 billion times Earth's atmospheric pressure at sea level. This tremendous pressure confines nuclear reactions to the stellar center, creating a region approximately 1/10 the star's radius where conditions support fusion. Outside this core zone, temperatures and pressures drop below fusion thresholds, and energy transport occurs through radiation and convection rather than nuclear reactions. The energy generated through fusion initially manifests as high-energy gamma-ray photons created in nuclear reactions. These photons cannot escape the star directly because stellar material remains opaque to high-energy radiation. Instead, gamma rays scatter repeatedly off electrons and atomic nuclei, gradually working outward while losing energy in each interaction. The random walk of photon follows from core to surface takes approximately 170,000 years in the Sun and somewhat less in the more compact Sirius A. As photons work outward through the star, they progressively shift to lower energies and longer wavelengths through repeated scattering. Gamma rays from fusion reactions degrade into X-rays, then ultraviolet, visible, and infrared photons by the time they reach stellar surfaces. The photosphere, the layer from which photons finally escape into space, radiates according to the star's surface temperature rather than the multi-million degree conditions where energy originated. Sirius A maintains energy equilibrium through a balance between fusion generation and radiative loss. The star produces approximately 25.4 solar luminosities, meaning it radiates 25.4 times more power than our Sun across all wavelengths. This enormous energy output requires fusing approximately 440 billion kilograms of hydrogen into helium every second, converting about 4.7 billion kilograms of mass directly into energy each second through the mass energy equivalence. The star's hydrogen fuel reservoir, approximately 70% of its total mass concentrated in the core, will sustain these fusion rates for roughly 660 million years total. Having already spent about 240 million years on the main sequence, Sirius A has consumed roughly 1/3 of its available hydrogen. The remaining 420 million years before core hydrogen exhaustion seems lengthy by human standards, but represents brief duration in cosmic time. Stellar structure equations govern how mass, pressure, temperature, and energy generation vary from a star's center to its surface. These coupled differential equations, derived from fundamental physics including hydrostatic equilibrium and energy conservation, allow astrophysicists to construct detailed stellar models predicting internal conditions based on observable properties like mass, radius, and luminosity. Models of Sirius A show a core region extending to approximately 25% of the stellar radius where fusion actively generates energy. Surrounding this core, a radiative zone transports energy outward through photon diffusion near the surface. A thin convective envelope develops where energy transport shifts from radiative diffusion to convective circulation as gas physically rises and falls in response to temperature gradients. Convection in stellar envelopes creates the complex surface phenomena observed as star spots, flares, and magnetic activity. However, A-type stars like Sirius A have relatively thin convective zones compared to cooler stars. This limited convection reduces magnetic field generation and stellar activity, making Sirius A a relatively quiescent star compared to more active objects like young solar type stars or red dwarfs. The chemical composition of Sirius A reflects both primordial abundances inherited from the interstellar cloud that formed the star and modifications from nuclear processing. Spectroscopic observations reveal hydrogen and helium as the dominant elements, comprising approximately 71% and 27% of the star's mass respectively. Heavier elements, collectively termed metals in astronomical usage, contribute roughly 2% of the total mass. Similar to solar metallicity, elements heavier than helium present in Sirius A originated in previous generations of stars. The Big Bang produced only hydrogen, helium, and trace lithium. Carbon, oxygen, iron, and all other elements formed through stellar nucleosynthesis in massive stars and supernovae that lived and died before the material that built Sirius accumulated. The star's near-solar metallicity indicates formation from well-enriched interstellar gas rather than pristine primordial material. Core fusion in Sirius A gradually increases the helium abundance while depleting hydrogen. The helium produced settles in the stellar center, slowly building an inert helium core that will eventually shut down hydrogen fusion. This process occurs continuously throughout main sequence lifetimes, creating compositional gradients that affect stellar structure and future evolution. Sirius B represents an entirely different physical state, no longer powered by fusion but radiating residual heat stored during its active lifetime. The white dwarf's interior consists primarily of carbon and oxygen nuclei embedded in a degenerate electron gas. Nuclear reactions no longer occur, having ceased when the progenitor star exhausted available fusion fuel and ejected its outer envelope. Electron degeneracy pressure supporting Sirius B against gravitational collapse rises from quantum mechanical principles governing fermion behavior. Electrons, being fermions, obey the Pauli exclusion principle requiring that no two electrons occupy identical quantum states when compressed to white dwarf densities. Electrons fill available energy states up to a Fermi energy level, creating pressure that depends only on density, not temperature. This degeneracy pressure allows white dwarfs to exist in thermal equilibrium without fusion. Unlike main sequence stars where thermal pressure requires continuous energy generation to maintain support against gravity, degenerate objects support themselves through quantum mechanical effects that persist regardless of temperature. A white dwarf can cool indefinitely while maintaining constant radius and density until reaching absolute zero temperature. The Chandrasekhar limit establishes the maximum mass a white dwarf can possess while remaining stable against gravitational collapse. This theoretical limit, approximately 1 point for solar masses, emerges from the balance between electron degeneracy pressure and gravitational compression. White dwarfs exceeding this mass cannot achieve equilibrium through degeneracy pressure alone and must collapse further, potentially forming neutron stars through electron capture processes. Sirius B, with its 0.978 solar masses, sits comfortably below the Chandrasekhar limit. The white dwarf maintains stable structure supported by electron degeneracy pressure operating at densities where typical values reached 1,000,000 grams per cubic centimeter in interior, somewhat lower at the surface. These densities create mean separations between atomic nuclei comparable to the Bohr radius, the typical size scale of atoms under normal conditions. At such densities, normal atomic structure cannot exist. Electrons separate from nuclei and move freely through the stellar interior, forming a degenerate electron gas. Nuclei arrange themselves in a crystalline lattice structure. Spacing determined by the balance between electron degeneracy pressure and Coulomb repulsion. Between positively charged nuclei, the interior of Sirius B resembles a giant crystal composed primarily of carbon and oxygen ions. Temperature in white dwarf interiors, while lower than during active fusion phases, remains significant. Sirius B's core temperature reaches approximately 5 million Kelvin, hot enough that nuclei maintain substantial kinetic energy despite the degenerate state. The surface temperature of 25,000 Kelvin, measured through spectroscopy, represents only the outermost layer where photons decouple from matter and stream freely into space. Cooling in white dwarfs occurs through photon emission from the surface, gradually draining thermal energy from the stellar interior. The cooling rate depends on the white dwarf's mass, composition, and surface temperature. Sirius B, having cooled for approximately 120 million years since formation, has decreased its surface temperature from perhaps 100,000 Kelvin or more to its current value. Theoretical cooling curves predict that white dwarfs with masses and compositions similar to Sirius B should decrease surface temperature at rates of approximately 50 Kelvin per million years at current temperatures. This cooling will continue over billions of years, eventually reducing the white dwarf to temperatures comparable to the cosmic microwave background radiation, approximately to 0.7 Kelvin. The energy powering Sirius B's current luminosity comes from heat stored in ions and residual thermal energy in the degenerate electron gas. As the white dwarf cools, ions in the crystalline lattice gradually lose kinetic energy, releasing heat that conducts to the surface and radiates away. The specific heat capacity of the degenerate matter determines how much temperature change occurs for a given energy loss. Crystallization of carbon and oxygen in white dwarf interiors releases additional energy as the material transitions from liquid to solid states. This phase change provides a temporary energy source that slows cooling, creating a plateau in the temperature evolution. Sirius B may have already undergone partial crystallization, or this process might occur in the future depending on exact internal conditions. Neutrino emission from white dwarf interiors contributes to cooling at a rate comparable to photon emission from the surface. High-energy photons in the stellar interior occasionally interact with electrons, producing neutrino-antineutrino pairs that escape the star without further interaction. These neutrinos carry away energy directly from the deep interior, creating an additional cooling mechanism invisible to external observations. Understanding the nuclear processes and quantum mechanical physics governing both Sirius components reveals the fundamental differences between actively fusing stars and degenerate remnants. These internal physics determine how each object radiates energy and evolves over time. Luminous extremes. Sirius irradiates energy across the electromagnetic spectrum from gamma rays to radio waves, though most power emerges at ultraviolet, visible, and near-infrared wavelengths determined by the star's 9,940 Kelvin surface temperature. The spectral energy distribution, a graph showing intensity versus wavelength, peaks in the ultraviolet portion of the spectrum near 290 nanometers according to Wien's displacement law relating peak wavelength to temperature. Approximately 40% of Sirius A's total luminosity emerges as ultraviolet radiation with wavelengths shorter than 400 nanometers, invisible to human eyes but detectable by specialized instruments. This intense ultraviolet output would prove hazardous to life, as we know it if Earth orbited Sirius instead of the Sun. The radiation could damage DNA molecules, destroy organic compounds, and sterilize planetary surfaces lacking protective atmospheres or ozone layers. Visible light accounts for roughly 35% of the star's energy output, concentrated in blue and white wavelengths that give Sirius its characteristic color. The human eye perceives this as brilliant blue-white light, noticeably different from the Sun's yellowish appearance. The color difference reflects the temperature gap between the two stars. Hotter objects appear blue while cooler objects look red. Following the same principle that makes hot metal glow red than orange then white as temperature increases. Infrared radiation comprises approximately 20% of Sirius A's total output, with the remaining 5% distributed across other wavelength ranges including radio waves and X-rays. The star's infrared emission, while less intense than its visible and ultraviolet output, provides crucial diagnostic information about temperature distribution, atmospheric composition, and surrounding environments. The absolute magnitude of Sirius A, measured at 1.42, places the star among the more luminous objects in our stellar neighborhood but far from the most powerful stars in the galaxy. Supergiants like Betelgeuse or Rigel achieve absolute magnitudes of -5 to -7, outshining Sirius by factors of thousands. Even among main sequence stars, A and B-type objects exceed Sirius's luminosity by wide margins. Nevertheless, Sirius A's luminosity of 25 for solar values represents remarkable energy output. The star radiates approximately 9.8 times 10 watts, nearly 10 octillion watts of continuous power. To provide perspective, this exceeds current human civilization's total energy consumption by a factor of approximately 300 trillion. The star produces in 1 second more energy than humanity has generated throughout all of recorded history. This enormous luminosity requires corresponding fuel consumption. Sirius A converts approximately 440 billion kilograms of hydrogen into helium every second, fusing more mass per second than exists in all Earth's oceans combined. The mass to energy conversion efficiency of fusion reaches 0.7%, meaning each kilogram of hydrogen fused releases energy equivalent to 7 grams multiplied by the speed of light squared, approximately 6.3 times 10 joules. The star's high luminosity relative to the Sun reflects its greater mass and the exponentially sensitive mass-luminosity relationship governing main sequence stars. Doubling a star's mass increases its luminosity by factors of 8 to 16 depending on the MASS range. Sirius A, at the point O to solar masses, follows this scaling closely, producing luminosity consistent with theoretical predictions for stars in this mass range. Surface brightness, the luminosity per unit stellar surface area, reaches values approximately 4 times solar for Sirius A. The star's larger radius partially compensates for its higher total luminosity, but the surface still radiates more intensely per square meter than the Sun's photosphere. This increased surface brightness combines with larger total area to produce Sirius A's substantial luminosity advantage over our star. Spectroscopic observations reveal that Sirius A's atmosphere contains hydrogen bomber lines at strengths characteristic of A-type stars. These absorption features arise when electrons and hydrogen atoms absorb photons while transitioning between energy levels, removing specific wavelengths from the outgoing stellar spectrum. The strength and shape of these lines depend on temperature, pressure, and elemental abundances in stellar atmospheres. Helium lines appear weakly in Sirius A's spectrum, indicating helium abundance lower than in B-type stars but higher than in cooler spectral types. The relative weakness of helium lines despite helium's high abundance results from ionization effects. At 10,000 Kelvin, most helium exists in ionized states where electrons have been stripped away, reducing the number of neutral helium atoms available to produce absorption lines in visible wavelengths. Metallic absorption lines from elements like iron, magnesium, and calcium appear throughout Sirius A's spectrum, providing composition diagnostics. The strength of these lines indicates that Sirius A contains heavy elements at abundances similar to the Sun, confirming formation from well-enriched interstellar material. Abundance patterns match those expected for stars formed from gas chemically processed through previous stellar generations. Sirius B's luminosity, while dramatically lower than its companions, still represents significant energy output. The white dwarf radiates approximately to 0.5% of solar luminosity, roughly 9.8 times 10 watts. This power output seems modest compared to main sequence stars, but remains substantial for an object no longer generating energy through fusion. The white dwarf's surface brightness far exceeds that of normal stars due to its tiny radius. Sirius B's surface area measures approximately 1/10,000th of the Sun's surface area. Yet the white dwarf produces about 0.5% of solar luminosity. Consequently, each square meter of Sirius B's surface radiates approximately 250 times more power than an equivalent area on the Sun's photosphere. This intense surface brightness results from the extreme surface temperature of 25,000 Kelvin, 2.5 times hotter than the Sun, according to the Stefan Boltzmann law. Radiative power per unit area scales with the fourth power of temperature. Doubling temperature increases radiative power by a factor of 16, while increasing temperature by a factor of 2.5 boosts radiative power by approximately 39 times. The white dwarf's spectral energy distribution peaks in the ultraviolet portion of the spectrum near 120 nanometers, far into wavelengths that Earth's atmosphere completely absorbs. Nearly 70% of Sirius B's total energy output emerges as ultraviolet radiation, with most of the remainder appearing in visible light. Infrared emission remains minimal due to the extremely high surface temperature, shifting peak emission to much shorter wavelengths. Gravitational lensing effects around Sirius B slightly modify the white dwarf's observed luminosity. Light emitted from the surface must climb through the intense gravitational field, losing energy in the process and shifting to longer wavelengths. This gravitational redshift means photons reaching distant observers carry slightly less energy than when emitted, effectively reducing the white dwarf's observed luminosity by a small but measurable fraction. The combined luminosity of the Sirius binary system, dominated overwhelmingly by Sirius A's contribution, reaches approximately 25.4 solar luminosities. Sirius B adds only about 0.63 solar luminosities to this total, contributing roughly to 0.4% of the system's radiative output. An observer viewing Sirius from a distance would see primarily Sirius A's light, with the white dwarf companion contributing only a faint additional glow. This luminosity disparity creates observational challenges when attempting to study Sirius B. The white dwarf's faint light drowns in the glare from its brilliant companion, particularly at visible wavelengths where Sirius irradiates most intensely. Separating the two components requires high angular resolution to distinguish them spatially, or observations at wavelengths where their brightness contrast decreases. Evolutionary path stars form from collapsing interstellar clouds where gravity overcomes thermal pressure and magnetic support, fragmenting diffuse molecular gas into dense cores that contract towards stellar dimensions. The cloud that produced the Sirius system collapsed approximately 240 million years ago during the late Triassic period on Earth, when dinosaurs were beginning their long dominance of terrestrial ecosystems. Initial collapse proceeds nearly isothermally, meaning temperature remains relatively constant even as density increases dramatically. This behavior occurs because forming protostars efficiently radiate away gravitational potential energy released during contraction. Infrared radiation from dust grains embedded in the collapsing cloud carries away heat, preventing temperature rises that would halt collapse through increased pressure. As density increases and the protostar becomes increasingly opaque, radiation can no longer escape efficiently and temperature begins rising. This initiates the second collapse phase, where rising temperature increases pressure, slowing but not stopping further contraction. The protostar continues shrinking while heating. Following theoretical tracks across the Hertzsprung-Russell diagram that plots stellar luminosity against temperature, the protostar that became Sirius accumulated mass rapidly by accreting material from its surrounding disk and envelope. In falling gas spiraled inward through a circumstellar disk. eventually settling onto the growing stellar surface. This accretion process released enormous gravitational potential energy, making young protostars far more luminous than they will be as mature main sequence objects of the same mass. Core temperature and pressure rose as the protostar contracted, eventually reaching approximately 10 million Kelvin, where hydrogen fusion ignited deuterium, a heavy hydrogen isotope present in trace amounts. Fused first at slightly lower temperatures than required for normal hydrogen burning. This deuterium burning phase provided temporary energy that briefly halted contraction before the star resumed shrinking toward main sequence conditions. True hydrogen fusion through the CNO cycle commenced when core temperatures exceeded 18 million Kelvin, establishing energy generation rates sufficient to balance radiative losses from the surface. The star achieved hydrostatic equilibrium, ending gravitational contraction and beginning its main sequence lifetime. Sirius A reached this stable state roughly 240 million years ago and has maintained relatively constant properties since. The companion that became Sirius B followed a different evolutionary trajectory due to its higher initial mass. Stars in the 5 solar mass range evolve much faster than to solar mass objects like Sirius A, exhausting core hydrogen in perhaps 50 to 100 million years rather than the billion-year timescales appropriate for slightly less massive stars. During its main sequence phase, the Sirius B progenitor fused hydrogen through the CNO cycle at even higher rates than current Sirius A, producing luminosity possibly reaching several hundred times solar values. The star burned brilliantly blue-white, far outshining its companion. The Sirius system during this phase consisted of 2 hot, massive blue stars, both radiating intensely and racing through their fuel supplies. Core hydrogen exhaustion arrived for the more massive star after approximately 50 to 80 million years. Fusion ceased in the stellar center as hydrogen depleted, and no other fuel could yet burn at prevailing temperatures and pressures, without fusion to provide pressure support. The core contracted while hydrogen shell burning ignited in a layer surrounding the inert helium core. This shell-burning phase drove enormous changes in the star's structure. The contracting helium core released gravitational energy that heated surrounding regions, accelerating hydrogen fusion in the shell. The increased energy generation forced the star's outer envelope to expand dramatically, cooling as it spread to larger radii while the total luminosity increased substantially. The star became a red giant, swelling to dimensions possibly exceeding 1 astronomical unit in radius. Surface temperature dropped to perhaps 3,000 to 4,000 Kelvin as the photosphere expanded, shifting the star's color from blue to orange or red. Despite cooler surface temperature, total luminosity increased because the vastly larger surface area more than compensated for reduced emission per unit area. During the red giant phase, the star may have engulfed any close-orbiting planets that existed in the original system. Material from the bloated envelope would have created drag on planetary orbits, causing them to spiral inward and eventually merge with the star. Only planets in orbits beyond approximately 2 astronomical units could have survived this phase. Core contraction continued throughout the red giant stage, rising temperatures and pressures until conditions became sufficient for helium fusion. At approximately 100 million Kelvin, helium nuclei began fusing through the triple alpha process, where 3 helium nuclei combined to form carbon. This secondary fusion phase generated new energy in the core, temporarily stabilizing the star's structure. Helium burning proceeded rapidly, lasting perhaps only a few million years. The available helium fuel, previously accumulated through hydrogen fusion, depleted as conversion to carbon and oxygen progressed. Some helium nuclei fused with carbon to produce oxygen, while others formed intermediate products. The star developed a carbon-oxygen core surrounded by a helium-burning shell and an outer hydrogen-burning shell. As helium exhausted in the core, the star lacked sufficient mass to ignite carbon fusion. Stars must exceed approximately 8 solar masses to achieve the core temperatures needed for carbon burning. The 5 solar mass progenitor of Sirius B fell short of this threshold, meaning stellar evolution reached a dead end with an inert carbon-oxygen core. The envelope became increasingly unstable as thermal pulses developed. Periodic ignitions in the helium and hydrogen-burning shells created temporary increases in energy generation, driving the envelope outward in pulsations. These pulses grew stronger over time, eventually becoming violent enough to begin ejecting material from the star's surface. Strong stellar winds, driven by radiation pressure on dust grains forming in the cool outer envelope, accelerated mass loss. The star shed its outer layers at increasing rates, expelling solar masses of material over thousands to tens of thousands of years. This ejected material formed an expanding shell around the remnant core, creating a planetary nebula visible from Earth as a glowing ring or bubble of ionized gas. Ultraviolet radiation from the hot stellar core ionized the ejected gas, causing it to glow in characteristic emission lines of hydrogen, oxygen, nitrogen, and other elements. The planetary nebula phase lasted perhaps 10,000 to 20,000 years before the ejected material dispersed and faded below visibility thresholds. The nebula dissipated into the interstellar medium, enriching surrounding space with heavy elements created during the star's lifetime. The exposed core that remained became Sirius B, a white dwarf with no remaining nuclear fuel and no capacity to generate energy through fusion. The white dwarf's mass, roughly 1 solar mass, contained primarily carbon and oxygen nuclei produced during helium burning. Trace amounts of heavier elements created during brief later fusion episodes or dredged up from deeper layers might also be present. Initial surface temperature when the planetary nebula dispersed likely exceeded 100,000 Kelvin, making the newborn white dwarf appear as an intensely hot, bright object despite its small size. Subsequent cooling has reduced the surface temperature to its current 25,000 Kelvin over approximately 120 million years, a time frame consistent with white dwarf cooling models. Sirius A remained relatively unaffected during its companion's dramatic evolution. The two stars' separation of tens of astronomical units meant that mass ejected from the red giant did not significantly pollute Sirius A's atmosphere or alter its own evolution. The orbital dynamics may have changed slightly as the system lost approximately 4 solar masses, causing orbits to expand according to conservation of angular momentum. Future evolution for Sirius A will follow the same general pattern its companion already completed, though on a longer timescale and with some differences reflecting Sirius A's lower mass. After exhausting core hydrogen in approximately 420 million more years, Sirius A will begin its own red giant transformation. The star will expand, possibly reaching several hundred solar radii while cooling to red giant temperatures. Helium fusion will eventually ignite in Sirius A's core after a period of red giant evolution. The star will burn helium for approximately 100 million years, converting it to carbon and oxygen while maintaining relatively stable structure. After helium exhaustion, Sirius A's envelope will also become unstable, leading to thermal pulses and eventual mass loss that creates its own planetary nebula. The final white dwarf remnant from Sirius A will likely contain between 0.6 and 0.7 solar masses, somewhat less than Sirius B due to the lower initial mass. This second white dwarf will emerge perhaps 500 to 600 million years from now, creating a binary system consisting of two slowly cooling white dwarfs locked in gravitational orbit. Both white dwarfs will cool indefinitely over timescales of tens of billions of years, far exceeding the current age of the universe. Eventually, both will become theoretical black dwarfs, completely cold stellar remnants that no longer emit detectable radiation. This final state represents the ultimate fate for all stars insufficiently massive to end in supernova explosions. The evolutionary stages connecting newborn protostars to final white dwarfs illustrate the life cycles governing stellar populations throughout the galaxy. Sirius provides a unique laboratory for studying these processes because we observe both an active main sequence star and an evolved white dwarf in the same system, representing different evolutionary stages occurring side by side. Observational history. Ancient civilizations recognized Sirius as the brightest star in the night sky long before any scientific understanding of stellar properties existed. Egyptian astronomical records dating to at least 3000 BC reference Sirius, which they knew as Sobdet, associating the star with the goddess Isis. The heliacal rising of Sirius, its first visibility in the dawn sky after a period of conjunction with the Sun, coincided with the annual flooding of the Nile River. This coincidence between Sirius's reappearance and the life-giving flood made the star crucially important in Egyptian calendars and religious observances. The Sothic cycle, based on Sirius's heliacal rising, provided a calendar correction mechanism more accurate than the 365-day civil calendar Egyptian administrators used for everyday purposes over centuries. The difference between the civil and Sothic calendars created observable drift that Egyptian astronomers carefully tracked. Greek astronomers cataloged Sirius among the most important celestial objects, giving it the name that survives in modern usage. The name derives from the Greek word Sirios, meaning scorching or glowing. Referring to the star's brilliant white-blue appearance, Ptolemy included Sirius in the Almagest, his comprehensive astronomical treatise compiled around 150 CE that remained authoritative astronomical reference for over 1,000 years. Ancient observations noted Sirius's color, though historical descriptions create some confusion. Multiple classical sources describe Sirius as red rather than the blue-white we observe today. Ptolemy characterized it as reddish, as did Seneca and other Roman-era writers. These descriptions conflict sharply with the star's current appearance and create a puzzle for historians of astronomy. Several explanations have been proposed for the color discrepancy. One possibility involves atmospheric effects, where observations of Sirius low on the horizon could show reddening from scattering similar to sunset reddening of the Sun. However, ancient writers distinguished Sirius's color from other bright stars observed under similar conditions, suggesting atmospheric effects alone cannot explain the descriptions. Another hypothesis suggests that Sirius B was still a red giant during classical times, and ancient observers saw the combined light of the blue-white primary and red giant companion as an overall red issue. This explanation requires that Sirius B became a white dwarf very recently in cosmic terms, within the last 2,000 years. Most stellar evolution models consider this timeline unlikely, but not completely impossible. The most probable explanation involves observer interpretation and language rather than any actual color change. Ancient color terminology may not map precisely onto modern color categories, and descriptions of bright objects might emphasize their fieriness or intensity rather than literal hue. Cultural and linguistic factors likely contribute more to the color descriptions than any physical change in the star itself. Systematic positional measurements of Sirius began in earnest during the Renaissance as astronomers developed better instruments and observational techniques. Tycho Brahe measured star positions to unprecedented accuracy in the late 16th century, though his instruments could not yet detect the subtle proper motion that Sirius displays. Edmund Halley, examining stellar positions measured over centuries, discovered in 1718 that several bright stars including Sirius had moved noticeably across the celestial sphere since ancient times. This proper motion, Sirius's relatively rapid movement against the background of more distant stars, indicated the star's proximity to our solar system. More distant stars show much smaller proper motions for the same space velocities, making high proper motion an indicator of nearby objects. Measuring the rate and direction of Sirius's proper motion became a priority for astronomers working to understand stellar distributions and motions. Friedrich Bessel's analysis of Sirius's proper motion in 1844 revealed the periodic wobble indicating a binary companion, the mathematical framework Bessel developed for analyzing stellar parallax. The apparent shift in stellar positions caused by Earth's orbital motion proved equally applicable to detecting orbital motion in binary systems. Bessel's work demonstrated that careful positional measurements over decades could reveal companions to faint to observe directly. The prediction that Sirius possessed an unseen companion represented a triumph of mathematical astronomy. Bessel calculated the companion's orbital period at approximately 50 years and estimated its mass at a significant fraction of Sirius A's mass. These predictions awaited observational confirmation, which came 18 years after Bessel's death. Alvin Clark's observation of Sirius B on January 31, 1860 confirmed Bessel's prediction and revealed an object that would challenge astrophysical theory for decades. Clark was not searching specifically for the companion but rather testing a new telescope by observing a bright, well-known star. The chance discovery illustrates how technological improvements often reveal unexpected phenomena. Early visual observations of Sirius B established its orbital motion and allowed refinement of orbital parameters. Astronomers measured position angles and separations between the two components, tracking their changing configuration as they orbited their common center of mass. These measurements confirmed the 50-year period and provided increasingly accurate determinations of the orbit's size, shape, and orientation. Photometric measurements attempted to determine Sirius B's brightness, complicated by the overwhelming glare from Sirius A. Observers estimated the companion's apparent magnitude at approximately 8.5, making it roughly 10,000 times fainter than its primary. This faintness explained why the companion remained invisible until relatively large telescopes became available. Walter Adams obtained the first spectrum of Sirius B in 1915 using the Mount Wilson 60-inch telescope. The spectrum showed absorption lines characteristic of a hot, white star, with surface temperature estimates near 25,000 Kelvin. This combination of high temperature and low luminosity created the theoretical puzzle that led to the concept of white dwarfs and electron degeneracy. The space age enabled observations impossible from ground-based observatories. The International Ultraviolet Explorer satellite, operating from 1978 to 1996, captured ultraviolet spectra of both Sirius components, revealing emission features lost to atmospheric absorption. These UV observations provided crucial data on photospheric composition and temperature structure. The Hubble Space Telescope imaged the Sirius system with unprecedented clarity beginning in the 1990s. Hubble's observations separated the two components cleanly despite their small angular separation and extreme brightness contrast. High-resolution images allowed precise position measurements and direct photometry of Sirius B without overwhelming contamination from Sirius A's glare. The Hipparcos astrometry satellite, operating from 1989 to 1993, measured Sirius's parallax with exceptional precision. The resulting distance estimate up to 0.6 for parsecs, equivalent to 8.6 light-years, reduced uncertainty in distance-dependent parameters like absolute magnitude and luminosity. Hipparcos also refined measurements of Sirius's proper motion and radial velocity. Ground-based interferometry achieved angular resolution rivaling or exceeding Hubble through technological advances in the 1990s and 2000s. Combining light from multiple telescopes creates interference patterns that encode information at spatial scales for smaller than individual telescope resolving power. Interferometric observations of Sirius measured stellar diameters and even detected surface features on Sirius A. The Chandra X-ray Observatory observed Sirius searching for high-energy emissions characteristic of stellar coronae or accretion processes. The observations detected faint X-ray emission from Sirius A consistent with coronal activity. Typical of its spectral type, Sirius B showed no significant X-ray emission above background levels, as expected for a white dwarf lacking active coronal processes. Spectroscopic observations accumulated over decades built comprehensive datasets on both components. High-resolution spectra revealed thousands of absorption lines corresponding to specific atomic transitions in stellar atmospheres. Analysis of these lines determined elemental abundances, atmospheric structure, surface gravity, rotation rates, and other physical parameters. Sirius A's rotation rate, measured through Doppler broadening of spectral lines, indicates an equatorial velocity of approximately 16 kilometers per second. This gives a rotation period of roughly 5.5 days for the star's 1.7 million kilometer diameter. The relatively slow rotation compared to rapidly rotating A-type stars suggests Sirius A may be viewed nearly pole-on or has genuinely slow rotation for its type.